Today, on how it's made. Honey, fiber optics, bricks, and pipe organs. It's Winnie the Pooh's favorite treat. It's sweet and sticky, and it's all produced by an industrious and intelligent insect whose miniature society is one of the most sophisticated in the animal kingdom. It all begins in a field where worker honeybees suck nectar from flower blossoms such as clover. They store it in their honey sac, then return to the hive where other worker bees suck it out and chew it, breaking down the nectar's complex sugars into two simple sugars called glucose and fructose. The bees then deposit the nectar into the cells of the wax honeycombs they've built. They fan it with their wings until most of its water content evaporates in the warm air of the beehive. What's left is thick and gooey honey. The bees then cap each honey-filled cell with beeswax. That's when the beekeeper steps in. Bees will sting if taken by surprise, so the beekeeper sprays the hive with smoke from burning pine needles, a scented warning that foreigners are about to enter the hive. Inside the hive are wooden frames hanging side by side, each holding a honeycomb. A hive can house hundreds of thousands of bees, all descendants of the prolific grand poobah of beedom, the queen bee. She's the big one in the middle. The queen bee lays up to 2,000 eggs a day, creating the workforce needed to feed and protect the colony. But the beekeeper tricks the colony's defenders. He replaces the hive's cover with a device called a bee escape, which smells like cherries. Bees dislike the scent, so most fly to the bottom sections of the hive. Another warning spray, and the beekeeper removes the bee escape. Now he can escape with the honeycombs. Inside the honey factory, they put the honeycomb frames on what's called an uncapping machine. Like a razor, it shaves the wax caps off the honey-filled cells of the combs. They scrape off the remnants manually. Then they set the frames on another machine called a honey extractor. It spins the honeycombs until all the honey is forced out of the cells. Afterwards, they filter the honey to remove any pieces of wax capping that slip through. Then, the honey is ready for bottling. Some beehives contain smaller frames designed to produce honey that isn't extracted from the honeycomb. Workers remove the frame and cut the honeycomb into pieces as is with a heated knife. That seals the wax around the honey inside. You eat it, wax and all. The beeswax lining of the honeycomb goes to make candles, furniture polish, lipsticks, and other products. When producers have more liquid honey than they can sell, they simply let it granulate, develop sugar crystals, and turn hard and white. Then, when the orders come in, they return it to its original liquid form by heating it to 130 degrees Fahrenheit. They vacuum clean the jars. Then fill them. One beehive can yield up to 7 pounds of honey in a single day. That's much more than the bees need for themselves. The surplus is what we end up eating. Honey production today is both efficient and humane. For centuries, the only way to harvest honey from hives had been to kill the bees. Then, in 1851, an American beekeeper invented a way to get the honey, yet spare the bees. His method, with the removable honeycomb frames, is the one we still use today. American researchers have invented a plastic that repairs itself when broken. Just apply heat, a simple hairdryer will do, and the break automatically mends itself. This could solve a long-time problem in electronics, because when components heat up and cool down, they weaken the plastic around them. Every time you talk on the phone or go on the internet, what you say or type travels to its destination through fiber optics, the process of transmitting voice or data via pulses of light through hair-thin glass fibers. Those fibers start out as large glass tubes. First, workers unwrap the tubes. Then they submerge them in a corrosive bath of hydrofluoric acid. That removes any oil residues. Then they set a tube into each end of a lathe. As the tubes spin, they're heated with a hydrogen-oxygen flame. When the glass turns white, it's getting close to hitting peak temperature. At 2,000 degrees Celsius, the two tubes fuse together. They put this new longer tube onto another lathe. As the tube spins, they inject a mixture of chemical gases inside, while a traversing burner heats everything up. The gas mixture contains liquid forms of silicon, an abundant chemical element found in nature, and germanium, a chemical element similar to tin that's used as a semiconductor in transistors and other electronic devices. As the gases heat, they undergo a chemical reaction that leaves a white soot on the inside of the glass tube. The heat fuses the soot, forming what will eventually become the core of the optical fiber. The glass tube itself will form the fiber's covering. When there's enough fused soot, they turn up the heat until the soot itself turns into glass. Then they heat the glass tube enough to soften it, as well as the new glass inside. The intense heat eventually makes the tube collapse on itself to form a solid rod. The internal structure of the optical fiber has been achieved. But it's in the form of a big bulky rod called a preform, so the next step is to thin it out. First, they excise the preform from the uncollapsed section of the glass tube. Then they install it vertically into the drawing tower, which will draw out the final shape. The drawing tower's oven heats one end of the preform to 2,000 degrees Celsius. The glass softens. Gravity helps pull it down, like honey dripping from a spoon. Then, using a glob of glass as a weight, they stretch the soft glass and keep stretching it until they formed a thin glass fiber. A series of pulleys measures the tension on the fiber as it's being drawn. A special monitor makes sure the fiber's precisely the right diameter, 125 micrometers. That's about 1/8 of a millimeter thick. Then the fiber passes through UV lamps that bake on an acrylic coating to protect against dust and other contaminants. Finally, the fiber is rolled onto a drum. From here, it's either shipped out as is or put into a cable. Fiber optic cables are expensive to produce, but they're smaller and lighter than traditional copper cables. They carry more information and need fewer repeaters to keep the signal from deteriorating. And unlike copper cables, they're immune to electromagnetic interference. They're also hard to tap without being detected. And all this is made possible by a complicated process based on a very simple principle: light traveling through glass. Those three little pigs knew what they were doing when they built that brick house. Not only are bricks wolf-proof, they're also fireproof, pest-resistant, and weather-resistant. No wonder they're one of the world's oldest building materials. Bricks are often made of shale, a lightweight rock that splits easily into thin layers. Quarry machines dig 40 centimeters down to expose the shale to the elements for 2 years. This weakens it, making it easier to process once it gets to the factory. A 4-foot-high stone wheel with a steel tire grinds the shale into powder. It grinds up 50 tons of shale per hour. A screen sifts out any pieces that need more grinding. The powder goes to the pug mill, which mixes it with water. This makes a thick paste that will next go through the extrusion machine. The extruder forces the paste through a rectangular opening to form one long continuous piece called a slug. At the same time, it shaves off the crustier top layer to expose what will become the face of the brick. If this gray shale mixture is fired as is, it'll naturally produce a red brick. To engineer a different color, they coat the slug in sand mixed with an oxide mineral such as zinc or iron. Next, they texture the surface with a textured roller. This is just one of many popular designs. Then, a large knife comes down like a guillotine and slices the slug into 5-foot lengths. You might be wondering where those 3 holes came from. Well, remember how the paste goes through the extruder to form the slug? Inside are 3 pins. They make 3 holes designed to decrease the brick's weight. Out of each 5-foot length, they cut 20 3-inch bricks. The ones on the ends are uneven, so they go back into the mix to make new slugs. Next comes the delicate job of stacking these newly minted bricks to be. A machine first separates them. Then, using inflating bags, it grasps them, raises them, and then stacks them. Meanwhile, the water in the bricks is starting to evaporate. To hasten that process, the bricks go into a dryer for 2 days. The dryer gets its hot air from the heat generated by the kiln, where the bricks go next for firing. The kiln is really a giant oven. It fires the bricks at 1,040 degrees Celsius. That's almost 2,000 degrees Fahrenheit. One and a half days later, the bricks are ready. The transfer machine takes them out of the kiln. But before they go to market, a technician does a quality check. He weighs and measures a sample to see if it meets the design specifications. Bricks are supposed to absorb some water, but not too much. Yet if they repel water completely, they'll also repel the wet mortar the masons use to stick the bricks together. So to test absorbency, the technician breaks a brick in half. He weighs it before and after, soaking it in water for 24 hours. By comparing the weights, he can see how much water the brick has absorbed. Once the batch gets the okay, they stack the bricks into cubes of 500 to 600. Each brick weighs 5.5 pounds, so each cube weighs in at about 1/4 ton. Brick is one of the sturdiest building materials around. It doesn't rot, fade, warp, or dent the way some other materials can. Bricks are also energy efficient. They absorb heat to help cool your house in the summer and hold heat to help keep it warmer in the winter. The music it makes is as complex as it is majestic. The pipe organ is one of the largest and most technically sophisticated instruments. Building one is an incredible feat of engineering and craftsmanship. Early man discovered he could make music by blowing across hollow reeds of different lengths. In ancient Egypt, an engineer devised what would later become the basic technology of the pipe organ, a steady airflow without mouth blowing, while controlling the air to each pipe to create different notes. By the Middle Ages, the pipe organ was a fixture in churches throughout Europe. Johann Sebastian Bach composed his greatest works for organ while working as the musical director of a church. A concept artist creates the design. The design then goes to a draftsperson who prepares the technical drawings. The organ's pipes are made of a mixture of tin and lead. Tin, the harder metal, gives brightness to the sound, while lead, the softer metal, gives it warmth. Artisans pour the molten alloy into a tray, then draw it out to form a sheet. As the sheet cools, the two metals react to each other, creating spots. The sheet goes into storage to give the alloy time to stabilize. 2 to 3 months later, it's ready to be formed into organ pipes. First, they cut pieces of metal in the shape of each pipe using templates and large rulers. Then they roll each piece using a mandrel. The larger the organ, the more pipes it has. Pipes are grouped in sets of 61, corresponding to the 61 black and white keys on the keyboard. An elaborate organ can have more than 10,000 pipes. The pipe maker carefully seals the body of each pipe by hand, using tin solder. Next, he solders the body of the pipe to the foot and languid. The languid is the part that produces the pipe's sound. The process of giving a specific sound to each pipe is called voicing. This work is done by a trained musician called a voicer. He enlarges the mouth of the pipe, called the cut-up, until it's approximately a quarter of the width across. He adjusts the pipe some more, blowing air through it to judge how to further refine the tone. Next come the wind chests, also called the soundboards. These are the large wooden boxes filled with air on which the pipes stand. Under each pipe is an air channel covered by a valve. The valve is made of leather and sits on a wooden board. When the organist pushes a key on the keyboard, the corresponding valve drops down like a trapdoor, releasing air into the pipe to play the note. They glue the valves to the wind chests one by one using animal glue. It's suppler and dries faster than synthetic glue. The valves are connected to the organ's keys mechanically by long tracks of cedar wood or by electrical wiring. The electric signal triggers electromagnets to cause a sudden air depression, making the trapdoor valve drop down and let the air in. The console is the organ's brain. It contains all the controls for the keys and sets of pipes. The organ's white keys are made of lindenwood covered with bone. The black keys of ebony or rosewood. An artisan adjusts the keys using a weight. When the weight rises, the tension is just right. The console, keys, and all the other components are finally put together in the assembly room. After testing, they disassemble the organ and ship it to its destination, where it's reassembled. The voicers come on site to perform what's called tonal finishing. They check and adjust each pipe according to the acoustics of the room. This process can take many months for a large and elaborate organ. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.
You're watching Discovery Channel.